Hi, my name is Arthi Padmanabhan, and today I'm going to talk about Reducto, a system for filtering frames on cameras to make real-time video analytics more efficient. This is joint work with Yenchi, Pengzhen, Yufei, and my advisors Harry and Ravi from UCLA. Recently, there have been two major trends in video analytics. One is that cameras are becoming pervasive, with applications ranging from traffic to security to retail and beyond. With more cameras, that means that the amount of video data being generated is also increasing rapidly. Simultaneously, what we're able to do with that data is getting more advanced. The machine learning and computer vision communities consistently come out with new models that can detect objects with higher accuracy, detect more types of objects, and even do advanced tasks like identify luggage that's been left alone at an airport. These trends have given rise to this type of pipeline that allows users to ask questions or queries on live video. We have a camera sitting at, say, a traffic intersection that sends all frames to a server where the frames are run through a deep neural network. This could be an object detector like faster RCNN or YOLO. It could be an object tracking DNN, a classifier, anything. And the result can be used to answer queries like, return the bounding boxes of all cars, or how many buses are there? Are there any ambulances? Where the responses are given per frame. The major goals of this kind of system are to, one, respond with high accuracy relative to the ground truth. So similar to other video analytics systems, when we refer to accuracy as a percentage, that's relative to running the full DNN over every frame in a video. And usually these types of queries are given with an accuracy target, which can be treated as a constraint. So essentially it's the amount of error the query can tolerate. So a query might say, with 90% accuracy, are there any ambulances? The second goal is to respond with low latency. Processing 30 frames per second is usually the goal because that's typically real time, which for context translates to spending about 33.3 milliseconds on each frame from the time the frame is recorded by the camera. Now, where this gets challenging is that achieving these two goals is extremely resource intensive, both in terms of network bandwidth and compute cost. If you want to send a single video at 1080p, you would need approximately 2 megabits per second, and if you consider that many such cameras are connected wirelessly, the bandwidth consumed adds up quickly. This causes network delays and makes it hard to respond to queries in real time. In terms of compute cost, while DNNs have been becoming more accurate, they've also gotten larger and more computationally expensive. Faster RCNN, for example, a state-of-the-art object detector, takes about 6 seconds to process 1 second of video on a Tesla P100, which is a $6,000 GPU. And both of these issues blow up further when you consider that an organization like a city or campus typically doesn't deploy a single camera in isolation. They'll more likely deploy multiple cameras on the same network, sending to the same server. So the predominant technique used for improving efficiency is filtering frames before they reach the expensive DNN. And the goal with filtering is to remove frames that don't meaningfully contribute to the query result. For instance, if we're tracking cars and there are no cars at night on a street, most frames can be dropped and results from previous frames can be reused. So the question we want to know is, what effect does this frame have on the query result? I'll go over the three main approaches to filtering based on prior work in order of most to least computationally expensive. The first one, used for example in Focus, is to insert a small object detection model, something like Tiny YOLO, into the pipeline as an approximation of the full DNN result. If that model gives a result with high confidence, we can just use that as the query response. If it's not confident though, then we send it to get processed by the full DNN. Another approach used by a few papers, including NoScope, is to filter based on the presence of certain objects. So if the query asks for the location of all cars, this method runs a small binary classifier to tell whether the frame has a car at all and sends it to be processed only if it does. The third approach is to calculate pixel level differences between a frame and the one before it, and only send a frame if it's sufficiently different. So we only really need to know when the query result changes. So if the previous frame had 5 cars and this frame is hardly different, we can reuse that result and be pretty sure that this frame has 5 cars as well. For all these approaches, the benefits we get from filtering are amplified when it's done on the edge or closer to the source. For example, from the network side, we save the bandwidth needed to send all those frames that were filtered out by any of these methods. So then the key question we're addressing in this project is, given the rise of smart cameras, can we take that to the logical extreme and filter frames directly on the camera? So given that we have some computational resources there, what kind of filtering can we do with them? Two things we need to know to answer that. One, what kind of resources are available on existing cameras? And two, how well do these existing solutions work on cameras? So to better understand what resources are on existing cameras, we analyzed the types of cameras available online from leading camera brands as well as state-of-the-art cameras designed with AI in mind. And we found that there's a wide range of cameras available. On the low end, you can pick up a Wisecam off the shelf for $20, and it comes with modest CPU resources. On the other extreme, the DNN cam ships with a full GPU on board and can run full DNNs on all frames in real time, obviously at a much higher price point. So the other thing we wanted to know is the types of cameras that existing deployments use. So where on the spectrum do they fall? And to that end, we analyzed publicly available information about deployments and conducted a study of local city and campus-wide deployments. And every deployment we found was on the left. So clearly, while the market is moving towards the right, we believe that given the cost of installation and maintenance, existing deployments will likely persist for a long time. To make our solution adaptive, we'll focus on the left end of the spectrum, but note that by focusing on cheap cameras, that doesn't preclude our techniques from being useful on more expensive cameras too. They would free up other resources and enable scaling to more videos and queries. Now we look at which filtering approach works best in this setting. We found that approximate models, though they're designed to be a lighter weight version of full DNNs, are still far too expensive to run on this type of camera. So Tiny YOLO ran at 0.6 frames per second, and recall that real time is 30 frames per second. Binary classifiers are fast enough, but they inherently miss a lot of filtering opportunities by only looking at whether an object is present or not. So if we look at these two consecutive frames and we're trying to count cars, binary classifiers would send them both because they both contain a car, when clearly the count doesn't change. Now, pixel level differences are able to sidestep these two issues, so we focus on those, but the paper contains more detail about comparing these three approaches. Pixel level differences come with a different challenge, and that is that it can be tricky to meet accuracy targets because they contain moderate amounts of noise. Recall that with frame differencing, we send a frame if the difference is above a certain threshold. Previous papers have done this by choosing the threshold by running the full DNN over part of the video, picking the threshold that meets accuracy while filtering the most frames, and using that threshold for the rest of the video. We tested this by analyzing 5% of a traffic video with an accuracy target of 90%. And we found that the accuracy over the rest of the video was less than 80%. We tried expanding the amount of video we used to pick the threshold, and still we fell consistently below 90%. We expanded this to more videos, and the results were similar. So it's really hard to pick a single threshold that works for a significant portion of video with respect to accuracy targets, and this just has to do with how dynamic video content is. So there are two fundamental things that need to be changed for frame differencing to work accurately and effectively. One is to choose the threshold dynamically. We saw in the last slide that static thresholds make it hard to meet accuracy, but to visualize why, let's consider two queries. One is counting the number of objects. The other is finding bounding boxes for the objects across 5 minutes of video. We plotted the optimal threshold, that is the one that filters out the most frames while meeting accuracy. Clearly, this threshold changes rapidly over the course of a video, which validates the idea of choosing it dynamically. Another reason accuracy can drop is because of relying solely on straight pixel comparison, because there are other low-level frame differences that are potentially more effective at picking up on changes between frames. For example, we could also consider looking at areas of motion and comparing their sizes. In this example, let's take the query to be counting cars. We can see that when the same car moves across a road in the top two photos, the value of area is quite low because the area of motion and its size remain relatively steady. When a new car enters, though, in the bottom two photos, we can see that the value of area is significantly higher because there's a new area of motion. we can see that Pixel didn't show that kind of contrast. In fact, it showed a higher value for the top. So that's one example where a direct pixel comparison doesn't pick up on these differences. So different features, we call these low-level differences features, pick up on different characteristics of videos. So we can see that a lot of analysis needs to go into making these decisions to get frame differencing right. And our two main challenges focus on how to do that. So how do we do this dynamic tuning of the threshold? And how do we know which feature to use? To answer those, we use this system design where the wimpy camera does only the cheapest work, the frame differencing, but its decisions on how to do that are guided by a server. We'll explain in the next few slides how the work is split between them. So to get the threshold, what we want to know is what is the threshold that filters out the most frames while meeting an accuracy target? To get this, we collect complete information for a small period of unfiltered video. We split the video into several second segments, and for each, we run the DNN over every frame and extract the differencing values between pairs of frames. And then for a wide sweep of thresholds, we record the diff, the threshold, the percentage of frames filtered, and accuracy. And since we only care about thresholds that meet accuracy, we then eliminate all entries that don't. In our case, that's 90%. And we aggregate the rest of the table by clustering diff values and getting this simplified hash table that maps diff value ranges to their optimal thresholds, a slightly conservative choice for their optimal thresholds to be sure that accuracy is met. So building this table is clearly expensive. We have to run the full DNN over every frame for a while and collect all this information. So that's a job for the server. Looking up the threshold, though, is super cheap. It's just a simple hash table lookup, so that can be done quickly on the camera. And that allows the camera to keep up with the rapidly changing threshold that we saw without waiting for instructions from the server. The next question we want to know is, how do we choose the feature? And to answer this, we similarly take unfiltered frames for a short period. We can get both the ground truth DNN results and calculate each differencing feature for all sets of frames. Then we consider a sweep of thresholds, and for each feature, we pick the threshold that filters the most frames while meeting accuracy, and then across features, we pick the one that filters the most frames. This is also fairly expensive, again, because we need to run the DNN over every frame. So we run this process on the server when a new query comes in. Now, one optimization to note here, this process could take over 10 minutes depending on how much video we want to use. So given that, this is something we don't want to do often and block each new query that comes in for that long. And to that end, we did a more detailed study across different videos and found that while the best feature changes across query types, it remains stable between videos. For our experiments, we used straight pixel comparison, comparing the edges within frames and comparing areas of motion, but note that other features can be added. We can see on the right that for the counting query, area filters the most frames while meeting accuracy across 3 different videos. And on the left, edge performs the best across videos for the bounding box query. And this goes back to the idea that each of these features operate at different granularities and capture different characteristics about videos. So importantly here, we only have to do this one time per query type, not per query or per video. Putting it together to form Reducto's system design, we have an offline step where we get unfiltered frames from the camera. And we use those to both decide the best feature done by a profiler and generate a hash table mapping diff values to thresholds. We send both of those back to the camera, and the camera now has all the information it needs to start filtering. Now with the camera, we can extract the feature, calculate the threshold, and only send frames whose diff is above the threshold to the full ML pipeline, or the full DNN. Now, so far, we've assumed that every time we look up a diff value in the hash table, we're going to have a hit in the table, meaning we've seen a diff value like this before. So what happens if we start getting some values that don't match anything in the hash table? This means that we're now seeing new content that we didn't see when the table was made. At that point, we'll pause filtering and send unfiltered frames again for a short period. And we'll regenerate the hash table using both old and new data. It's important to note that while this is happening, we're still responding to the query. In fact, we're responding with 100% accuracy during this time because we have ground truth data for these frames, just that we're not doing any filtering. So once we have our updated hash table, we can go back to filtering as normal. To evaluate Reducto, we considered three queries: detection, so finding bounding boxes; object counting, just the number; and tagging, which is a binary decision on whether there's any instance of the object or not, each for people and cars. We used 8 traffic videos taken from all over North America, and for each, we used 25 10-minute clips. On our server, we had YOLO v3 running as our object detector DNN, and for our camera experiments, we used either a Raspberry Pi Zero, whose specs matched the type of cameras we're targeting, or a VM with matching resources. We considered all these points when evaluating Reducto, and for this talk, I'm going to go over the first 3. How does Reducto's filtering compare with the offline optimal, that is the maximum potential filtering? How fast does Reducto run on a camera, and importantly, does it run in real time? And what kind of compute and bandwidth savings do we get from it? There's information in the paper about how it compares to state-of-the-art systems and a sensitivity analysis. So this graph shows the percentage of frames filtered or dropped, so the higher the better. We plotted the offline optimal, which is where the maximum number of frames are eliminated while meeting the accuracy target, in dark blue and gray for cars and people, and the percentage that Reducto filtered in light blue and gray. Across queries, we found that Reducto filtered a median of 36 to 51% of frames, while consistently meeting accuracy target, which for this experiment was set to 90. You'll see that Reducto's accuracy is higher than the optimal, and this is because where Reducto conservatively chooses the threshold to overshoot accuracy, the offline optimal perfectly hovers around the target due to knowing the ground truth. We ran Reducto on a Raspberry Pi Zero, which has 1 core, 1 gigahertz, and 512 megabytes memory, matching roughly the median of the type of cameras we're targeting. It was able to run at 47.8 frames per second, comfortably clearing the real-time mark. If we break that down, we see that it spends most of the time extracting low-level features from each frame, so for example, extracting edges. It takes some time to compare the frames, and the only function left is hash table lookups, which run extremely fast. As far as resource savings, let's first look at network. Recall that the benefit of filtering at the camera is that we save the bandwidth needed to send the filtered frames. We see that across the dataset, Reducto filters out about 53% of frames, which translates to 22% in savings in bandwidth. And the discrepancy there is due to how videos are encoded. Here it was H.264. And that's compared to 39% for offline optimal filtering. When we look at the effect on compute, we expect the frames per second value to increase with Reducto because for every frame we don't send, we reuse results that are already computed, so we don't have to run the DNN on those. And we can see that Reducto more than doubles the backend processing speed from 41 to 86 frames per second compared to the optimal of 140. And recall that early on, we said that the reason we care about network and compute costs is because they affect our ability to respond to queries with low latency. So now let's look at it end to end. With these network and compute savings, how did our latency change? We see that across different networks, including both fixed rate and time varying networks, Reducto reduces the median response time by 22 to 26%, and that's within 13% of the optimal. To conclude, Reducto filters frames on cameras using cheap frame differencing techniques. This is enabled by a camera server architecture to split light and heavy work, and the result is that Reducto filters out over 50% of frames and lowers latency by 22% while consistently meeting accuracy targets. Our code is open source and available at this link. Please email me or Yanqi Li at these addresses with any questions. Thank you.